Okay, so these notes are going to talk about nuclear chemistry. We're going to go into the history of radioactivity, what radiation is, the types, how to block it, all of those cool things. All right, so I just wanted to kind of give you some background on nuclear radiation and how we kind of discovered this stuff. This is Marie Curie. She was the lead scientist who was really researching what was going on with nuclear radiation. She did a lot of work with radiation and with radioactive elements. She actually died in 1934 from leukemia that was caused by long-term exposure to radiation. Her lab books are so full of radioactive elements. They've absorbed so much of this radioactivity that they're not actually safe for us to touch anymore. They're contained, and when we go to study them, we have to don whole suits to protect us from the radiation. So Marie and her husband Pierre both kind of worked on this radioactivity. He happened to pass away before she did, so she kind of continued the work and made a lot of the advancements and the discoveries. So they first started out looking at like the glass plates, the photo glass plates, and they saw some fogging, and they were wondering what that was caused by, and they realized that it was these rays that were emitted by uranium. So she worked a lot of her stuff with uranium. She called this radioactivity, and these penetrating rays or particles that were emitted, we called that radiation. We're going to start looking at nuclear reactions, and nuclear reactions are different from chemical reactions. If you'll remember, chemical reactions are when we take molecules and atoms and we're going to adjust them, kind of move some electrons around and make some new products, but still having the same atoms together. We just may change how they're sharing or giving and taking of electrons. Nuclear reactions are when we have isotopes that either have too few neutrons, so they don't have enough neutrons to kind of block that positive charge of the protons, or they have too many neutrons and we're shoving too much mass into that teeny tiny space that they're unstable. It's too much energy in there. So these are called radioisotopes, and they want to be stable, so they'll change. So we're literally changing the nucleus of an atom in a nuclear reaction. There are three types of nuclear radiation. We have alpha, beta, and gamma. Each of these have a unique particle or charge with them, and they all affect the body differently. To start off with, we're going to look at alpha radiation. In alpha radiation, we are going to release an alpha particle. Pretty easy to remember. Alpha radiation, alpha particle. An alpha particle is 2 protons and 2 neutrons. So you have this unstable nucleus, and it's going to get 2 protons together and 2 neutrons, pack it up nicely, and kick it out. Okay, well, in this case, we're changing the number of protons inside an atom. So we're changing the proton count inside this nucleus. We're changing that element. No longer is it the one it was before. Now it is 2 protons less. So you can see down at the bottom of the screen, we have the alpha radiation equation here, and we're going to start out with uranium. And so uranium, 238, which is radioactive. 2 of those protons are going to leave. 2 of the neutrons are going to leave. So if we take 2 protons out, the mass number is now 90. If you look on your periodic table, that's thorium. And then if we take out 2 neutrons, our mass number goes from 238 now to 234. Then we also have, because we can't have any particles just disappearing, we have what's essentially a helium ion is being released. We have a mass number of 4, so that's the 2 protons and the 2 neutrons. This is an alpha particle, is this helium atom, and it has a charge of +2 because there's only 2 protons in there. There's no electrons to balance that out. Next up in beta radiation, we are going to be releasing a beta particle. What this really is an electron. So we have this atom, it's unstable, the nucleus has way too many pieces in it, way too many neutrons, and so one of the neutrons is going to break apart. And it's going to form a proton, which is the positive charge, and then the electron, which is the negative charge. Well, that negative electron just gets shot right out of that nucleus to kind of to give us a little bit more space. And this electron is then a free beta particle that's just kind of floating around out there in space and can do some pretty big damage. If you remember, our electrons are the things that like help us make bonds, and they share and or give and take. And if we just got a couple extra floating around, that's not really great for our cells. All right, so here is an example of beta decay. And a really important one is carbon-14. There's plenty and plenty of carbon around. Most of it is carbon-12, so it only has 6 neutrons. In this case, it has 2 additional neutrons to make it carbon-14. That's too many neutrons in the atom. So it's going to break it apart. It's going to make a proton and an electron, and it shoots that beta particle out, the electron, and then it's got this extra proton kind of sitting there in the nucleus and one less neutron. Well, one more proton means that it doesn't have an atomic number of 6, it has an atomic number of 7. So it has now morphed into nitrogen and not carbon anymore. Our last type of radiation is called gamma radiation, and in gamma radiation we don't actually have a particle that's leaving, we have a ray. So it's like this little packet of high energy, it's called photon. It's kind of like a packet of light that just gets shot out of the nucleus when we have a nuclear reaction. This can sometimes happen during beta radiation or during alpha radiation. Our example we have here is gamma ray that's produced during an alpha radiation. So we start out with thorium, which is 230. We put together that little alpha particle, and in doing so, we're kind of lessening the amount of energy that's inside that atom and inside that nucleus. So, well, we know that energy is conserved, and if we had the energy inside the nucleus to begin with, it's got to go somewhere else. And in this case, it forms a gamma ray and it's shot out. These are so teeny tiny because they're not really a particle, that they're very penetrating, and they can be the most damaging to a person or anything really. These will go pretty deep and do some major damage to vital organs and cells and that sort of thing. Speaking of penetration, here is a nice diagram that shows we have the pink is alpha, the blue is beta, and the black is gamma, and you can see what will stop these different radiation levels. So alpha, it's pretty big. We've got 4 pieces in there, 2 neutrons, 2 protons. Even something as small as a piece of paper can stop that. And really, if you think about UVA and UVB rays from the sun, we're trying to stop those alpha particles from the sun coming into our skin. And so something even as thin as sunscreen can protect us from the alpha particles from the sun and protect our skin. So it's really easy to stop alpha. Beta is not so easy. We need a little bit thicker material to do it, but again, a beta particle is an electron, so once we start putting quite a few atoms in between us and the beta particle, then we can get it stopped. We'll get that electron kind of wrapped up into another atom. So something as thin as even just kind of a sheet of wood, like some plywood, can stop beta particles. But notice that the gamma rays are able to easily go through the paper, easily go through the wood. That's because they really don't have a mass. So they can just shoot right through things because there's nothing really there to stop them. So we need to get kind of lead or concrete. What I like to think of is kind of Superman with his kryptonite. You know, you put it in that little lead box and it can't harm Superman. And then you open it up and then, Superman's all totally, weak because he's around kryptonite. I think kryptonite probably has a lot of gamma rays to it. You close that up, keep it behind a couple inches of lead, and you're good. You're protected from it. This would be why we have fallout shelters for, big nuclear bombs and all that kind of thing. We want to put quite a bit of concrete between us and the bomb that's going off, so the big bunkers that were built way underground into the Appalachian and Rocky Mountains to protect people from the gamma rays that would be emitted if we ever used a nuclear bomb on American soil. Okay, so I've had a couple of these examples on a few of our screens so far, and I just kind of want to talk about how I make up these reactions when we're looking at something decaying. What we need to pay attention to is the mass numbers and the atomic numbers have to be equal on both sides of the equation. So I've highlighted here that the mass numbers need to be equal. Well, we have 230 on the left side of the equation, and we have only 4 and A on the right side of the equation. So we need to figure out what A is to make that side equal to 30, or 230. So we take 230, subtract out 4, and we get 226. We also need the atomic numbers to be equal. So we have 90 on the left side of our equation, and we have 2 and Z on the right side of the equation. So since we need those to be equal, our Z has to be equal to 88. So 2 plus 88 gives us 90. If we look at our periodic table, 88 on the periodic table is radium. So we've taken thorium and we've turned it into radium through our nuclear decay. So here's another example where we're going to take gallium and we're going to go through beta decay. This is when we have that electron coming off. So we're going to need to make sure that our numbers on top and our numbers on bottom are balanced. If we start out with 68 on the left side and we have 0 and A on the right side, obviously we're going to still have 68 as our mass number for that X element off to the side. For our atomic numbers, on the left we have 31, on the right we have -1. So -1 plus Z has to equal 31. So we need to go up to 32. In this case, 32 as an atomic number is germanium. So we've taken gallium and we've changed it into germanium. Looking at this example, we start out with a mass number of 242 on the left and only 4 on the right. So we need to come up with 242 minus 4. By subtracting those, we come up with a mass number of 238. Now we need to look at 94. 94 on the left side and only 2 on the right side. This gives us an atomic number of 92 for our new atom. If we look on the periodic table, this new atom is uranium.